So we've already done about half of this, maybe a third of this trig substitution lecture. We're going to finish the rest today. Remember that what we are trying to accomplish here is to transform our starting integral, like the 1 over square root of 16 minus x squared, into something that we can integrate. This one we couldn't with any kind of normal, regular substitution. So what we're doing is something called reverse substitution. We let x equal some function of another variable, and then see what dx is, plug it all in, and see if the thing that we end up with is easier to integrate. And so in this section, we're using trig functions. And I've got for you at the bottom of the second page some suggestions on which trig functions to use and when. The first thing is, if it's a square root of a number minus x squared, you can use x equals a sine of theta, where a is the square root of that first number. So like on our first problem, it was 16 minus x squared. So we used a 4 sine theta. On a problem that might have a number plus x squared, or even x squared plus a number, because order doesn't matter with addition, I would use a tangent of theta, and then the result is when I plug that into a squared plus x squared, I can use the identity over here to turn that thing into something with a secant squared. Okay? Now that's best if it's not under a radical, because secant squared is the derivative of tangent. And so if it just shows up as a secant squared, maybe we can integrate it. That's what we hope for at least. And then square root of x squared minus a squared, so it's reverse of a squared minus x squared. If it's the other way around, then the best choice is a secant theta. And we try that, we plug it in, then we see if any trig identities help us to simplify the integrand. Okay, so let's use our newfound skill set to find a formula for something that, to me, sounds like an interesting question that I don't know if I even know the answer to off the top of my head. Find the area of an ellipse. You know how to find the area of a circle, pi r squared, easy. So if I've given you an ellipse, and this is a formula for ellipse that comes out of algebra. This is the conic section. Okay. General formula for an ellipse. X squared over a squared plus y squared over b squared equals 1. Have you seen that before? I hope you have. If not, just take for granted that the solution set to that guy is this ellipse over here. It's a radius of x in the x direction, in the x direction. So this distance here is a, and this distance here is b, and then it's that oval shape that you get. Okay? So let's see if we can't find that. Now, first thing I'm going to do is turn this into an area under a curve problem. So if that's the case, what would you do first to find the area of an ellipse using calculus? Okay, so you're solving for y, exactly. So I want this in terms of y equals something in terms of x, right? All right, so Kyle said let's move this over here, which gives me y squared over b squared equals 1 minus x squared over a squared. Multiply by b squared. Actually, one thing I'm going to do here is I want to combine that into one fraction just for simplicity's sake. Find a common denominator and combine those. That gives me, just write this as 1 over 1, right, and a squared over a squared. I get a squared minus x squared over a squared, right? Now, multiply that b across, and I get y squared is equal to a b squared over a squared times a squared minus x squared. Right? If I move this b over here, it just becomes b squared times that. I'm just writing this together out front, and an a squared minus x squared. And square root, so y is plus or minus the square root of that whole thing. Now go ahead and take the square root of b squared over a squared and get b over a, but I'll leave the other thing inside the radical because you can't take the square root of different parts of a subtraction problem. So it's just a squared minus x squared. So the top part of this curve that I've drawn here in blue, that would be b over a square root of a squared minus x squared. And then the bottom half of that curve would be the negative part, minus b over a square root of a squared minus x squared. So one way to find the area of this ellipse would be to basically take the top curve minus the bottom curve, area between two curves, right? So I could take this top curve up here minus this bottom curve down here and integrate from, well, see, if this is a comma 0, then this one is negative a comma 0, right? So negative a to a, top curve minus bottom curve. Which I could do, and I would get the same answer. But it actually turns out to be slightly simpler to recognize just a geometric property of this thing. I could also find the area of the shaded region and just multiply it by 4, which would be a slightly simpler integral because it wouldn't have a radical minus a radical. It would just be, if I wanted to find the area of the blue, that would be the integral from 0 to a, right, from here out to here, of just the area under the top curve, right? So b over a square root of a squared minus x squared dx. So what I'm claiming then is that the area of the ellipse would be 4 integral 0 to a b over a square root of a squared minus x squared dx. And that's what I need to find. That's the integral I need to take. If I can find that, and then multiply it by 4, I will have the area of an ellipse. I'll have a formula. And it'll depend on whatever a and b would be. Right? I got the a and the b in the formula now. Okay, so how do we find that integral? Do you recognize it? It's a trig substitution, right? Because you've got a square root of a squared minus x squared staring you in the face. So what would I let x be? Use trig substitution. Let x equal, which one? Sine. So a sine theta. Dx is then what do you say in your head? The derivative of sine is cosine. The derivative of sine is cosine. Derivative of sine is cosine. That's how I remember all the other things, whether it's the integral, whether it's the derivative of sine, derivative of cosine. That's the one thing that I say in my head over and over again. Derivative of sine is cosine. So all I need to get the sine right is that one, right? D theta. All right, so let's plug all of that in. Well, actually, I tell you what, let's do the two things that we normally do here. First of all, solve for theta, which means theta would be, if I divide the a across, actually I'll just write it, sine of theta is x over a, which means theta is sine inverse of x over a. So that's just preliminary work in case I need it. The other thing I'd actually go ahead and have us do, just in case we need it, You don't always have to do this, but I like to anyway, so I'm going to do my triangle. Draw the triangle. Now, what triangle am I talking about? It's the triangle with this theta in here. Now, if sine of theta is x over a, where are my x and a on that triangle? Opposite and hypotenuse. So that's opposite over hypotenuse. So I put an x here and an a here, which leaves the other side to be square root of a squared minus x squared. It's the thing that's in the radical. And last of all, let's simplify square root of a squared minus x squared. With our substitution. That makes this square root of a squared minus a squared sine squared of theta. So what's that equal to? You're seeing that we've got an a squared in both of these, right? So we can factor that out. And then you're left with the 1 minus sine squared, which becomes your cosine squared. So factor out the a squared. That makes this a squared cosine squared of theta. So that's just a cosine theta. Now, I think I have all the pieces I need to put it together. All right, so let's come back to the integral. This is now 4 integral from a to 0. Nope, 0 to a. I don't know why I did that. 0 to a of b over a times a cosine theta times here it is, a cosine theta d theta. Now, I didn't make a big deal about it. Let me just say it one more time. This integral that I had up here, I wouldn't be able to integrate with substitution or any other technique that we have so far. This is the only thing that gets it into something that I can integrate. So, I'm throwing this substitution at it, and I want to see if the result is something I can integrate. All right, so simplify the integrand. What do you get? A's cancel. You've got another a here. So I'm going to write that as a times b. And cosine times cosine is cosine squared theta d theta. Now, is that something you know how to integrate? Where have you seen that before? Do what? Yeah, section 2. The previous section we covered from this one. When you had odd powers of sines and cosines, that was where you strip things off. When you had even powers, that's where you use the double angle formula. Okay? So now we're going to use cosine squared of theta is 1/2 1 plus cosine of 2 theta. So this is now 4 integral. Actually, can I pull that as a AB outside? Is that okay with you guys? Since it doesn't depend on theta, I'm going to bring it out there. 0 to A, 1/2 times 1 plus cosine of 2 theta d theta. Now what? So take the 1/2 out, sure. So I've got 2AB, integral from 0 to A, 1 plus cosine of 2 theta d theta. And now? Integrate it. Integral of 1, theta. Integral of cosine. Because the derivative of sine is cosine. If you reverse that, it's just an integral of cosine is sine. So it's the same sign, and it's going to be a sine of 2 theta, but that would be wrong, because if I took the derivative of that, I'd get a 2 out front, so I need a 1/2 to cancel that out. Integral of cosine 2 theta is 1/2 sine 2 theta from 0 to A. Oh, we screwed up somewhere. Completely forgot one step. Oh, I made a mistake. Let me highlight where we made a mistake, and you tell me why it's a mistake. We forgot to change the limit. Substitution problem. You always have to change 3 things, right? Integrand, differential, and the limits, right? Theta doesn't go from 0 to A, does it? What goes from 0 to A? X does. Oh. Did you do this in pencil? I hope you did this in pencil. Oh. Boom. Boom. Oh. I just got to change my limits all the way through. I recognized we were going to have a problem when we started plugging in A inside of a sign. That wasn't going to simplify at all. Okay. Change the limits. So how do we find the limits? Well, we remembered that x is equal to a sine of theta, right? So we've got to plug in our different limits in for x and see what we get for theta. We need to know what theta is that goes with each of those x's. So if x is 0, I get a sine theta. Actually, I guess the easiest one to use is my formula over here, right? This formula up here. Why don't I just use theta is equal to sine inverse of x over a. Sine inverse of 0 over a. Sine inverse of 0. What angle, if you take its sine, gives you 0? It's 0. And what's sine inverse of a over a? Or sine inverse of 1? It's pi over 2. Right, when your sine wave goes up and then back down and over a course of 2 pi, right? That's halfway between 0 and pi that you get up here. So 0 and pi over 2. 0 to pi over 2. 0 to pi over 2. 0 to pi over 2. And 0 to pi over 2. Zero to pi over 2. Now, plug in our limits. 2ab pi over 2 plus 1/2 sine of 2 times pi over 2. All of that minus 0 plus 1/2 sine of 2 times 0. All of this here is 0. Sine of 0 is 0. 2 times pi gives me, 2 times pi over 2 gives me just pi. Sine of pi is 0. So I get 2ab times pi over 2, or ab pi. Isn't that nice and neat? The area of an ellipse is a times b times pi. Does that make sense to you, that the area of an ellipse would be ab times pi? Well, think of it this way. A circle is just a special kind of ellipse, right? What's special about the ellipse when it's a circle? A and the B are the same, right? So say they're both r. What does that formula give you? Pi r squared. An r times pi, pi r squared. Works. And now we've got a much more general formula that works for any ellipse. You just multiply the two radii together times pi. And we've now proven it with calculus. Isn't that beautiful? Now you don't have to. Don't have to accept. All right, let's do some more. I'm impressed. I thought that was pretty slick. Now I know. And I believe it. And I don't believe it because somebody told me. I believe it because I've seen it with my own eyes. I've done it with my own hands. All right. What would you use as a substitution on this one? X squared plus a squared. Tangent. So let x equal what tangent of theta?
2.
Square root of this guy, right? So if a squared is 4, then a is 2. That's all I'm saying there. You don't have to write that down. It's just messy. You see where I got the 2? Yes? Okay. Now, dx then is... Other things I like to do in this process are solve for theta.
So we don't have to keep the square root sign?
I haven't done anything to replace the integrand yet. All I've done is suggested a substitution and identified what I'm going to do with my differential. In a minute, I'm going to simplify the integrand. Okay. Tangent inverse of x over 2 is my theta. By the way, you may have not noticed it or paid attention. When I do this solve the theta part, or when I do the build the triangle part, I don't always need that information. I turned out to need sine inverse of x over a in this problem above because I needed to change my limits. That's not the only time it ever shows up. If you go back up to the problem we did very first, my answer had just a theta in it. And so in that problem, I needed theta solved for just to plug in to my answer. So this kind of preliminary work that I'm doing up front isn't always needed, but usually is. So that's why before I do anything, I choose my substitution, I solve it for theta, I solve it for my other variable. I also usually build my triangle at that point. On the previous problem, the ellipse problem, I didn't need that triangle at all. But on the problem before that, I needed the triangle to figure out what cotangent of theta was. I had set up x is equal to 3 sine of theta, and then later my answer had a cotangent of theta. So I needed the triangle to figure out what is that in terms of x. So that's why when I do my substitution, I find the x, 2, I solve for theta, and 3, I draw my triangle. So where is, what parts of the triangle do I know in this case? That's opposite over adjacent. So this is x, and this is 2, which makes this up here, the hypotenuse, what? X squared plus 4, right? Notice how that's actually the thing that's in the radical. It just always works out that way. It's nice. Okay. Now let's simplify square root of x squared plus 4. So maybe before I say I simplify the integrand. So that makes this 4 tangent squared theta plus 4. All I'm doing is, looking at this radical, I plugged in 4x, x equals tangent, or 2 tangent of theta. And that gives me this. And then I can factor out the 4. And I get tangent squared of theta plus 1. Which is secant squared. So 4 secant squared theta, which is 2 secant theta. All right, now let's try the integral. So x squared here becomes 4 tangent squared of theta. The radical we just showed is 2 secant of theta. And dx is remember that the dx is essentially on top of a fraction. It's not on bottom. So one of these will cancel with one of those. The 2 will cancel. So I'm left with, what's left behind? I've got a secant theta on top and a 4 tangent squared of theta d theta. And that's not great. If I tried a substitution there, the only 2 choices for substitution would be either secant or tangent. If I use secant, my du has to have a secant tangent, because the derivative of secant is secant tangent. I don't have that. If I use tangent, then I need a secant squared. I've only got a secant to the first. Okay? So substitution doesn't help. If all else fails, in trig, convert everything to sines and cosines. Okay? I don't know if you learned that whenever you were doing your trig identities when you took pre-cal or trig, but that was one of those basic rules. If all else fails, change everything back into sines and cosines, because every trig function can be written in terms of sines and cosines. So that's my next trick, my next try, my next attempt. It's like a sledgehammer to hit your trig functions with. Okay. Can I pull the 1/4 out? Is that okay with you guys? Sure it is. You know you want me to. I don't know why, but I get the impression every time I do that, or I guess every time I don't, I think Matt yells at me and tells me to take something outside. So I'm going to do that just because he's made such an impression on me. All right, 1/4 outside. So the 4 is not there anymore. What is secant the same thing as? 1 over cosine. And what is tangent the same thing as? Sine over cosine. So sine squared then over cosine squared theta d theta. I think I'm seeing a light at the end of the tunnel here. Okay, so I've got 1 over cosine theta times cosine squared theta over sine squared theta d theta. That's gone, and I got down to 1 cosine. It's a cosine of theta over sine squared theta d theta. If the cosine had gone away, then I would have had a cosecant squared, which I think I have a formula for. But I still got the cosine in there messing things up. But now let's go back to the same thing I was talking about before. Up here I said, what could we possibly try for substitution? I could try u equals secant or u equals tangent squared. Neither one of those would work. But can I use maybe a substitution here? If I use u equals cosine, then I need a sine up on top, but my sines are on bottom. But if I use u equal sine of theta, which gives me a u squared on bottom, and then what's my du? Oh, the angels start to sing. You hear them? Did you hear that? They sounded better than I did whenever I tried to do an impression. It's like a chorus is opening up above us because, wow, there's the du and there's u squared. So I've got now 1/4 the integral of 1 over u squared du. And there is a easy little integral to do. Right? 1/4 integral of u to the minus 2 du. We cracked it. We cracked the nut with a substitution, changing things to sines and cosines, and then another substitution. What's the integral of u to the minus 2? Add 1, divide by it. Negative 2 plus 1 is u to the minus 1 with a minus out front, right? Or divide by minus 1 is just multiplying by minus. Plus c. So, minus 1 over 4. This right here. So, sine of theta to the minus 1 plus c, or negative 1 over 4 sine of theta down here on bottom, plus c. Now I got 2 ways to go about this. One, I could just go straight into my triangle and plug back in what sine of theta is. Or I could recognize what's 1 over sine theta, the same thing as cosecant. Yeah. Cosecant of theta plus c. Now I go to my triangle. You got to have your answer in terms of x, so we can't stop there. So now we go back up the triangle that we built. And cosecant is over opposite. Hypotenuse over opposite. So I get negative 1/4. Hypotenuse was square root of x squared plus 4 divided by x. That's your opposite, all plus c, or negative square root of x squared plus 4 over 4x plus c. There is your integral. All right, so you leveled up now. That's more XP points for you right there because you've mastered another layer of trigonometric substitution.
Level 2,
I mean, every level gets harder. I mean, and this is that next level, okay?
Okay, so the question I have for you is, when we do the ellipse, should it be a d pi plus c?
Definite integrals don't need a plus c. Because when you plug in the two limits, it's like a plus c and a plus c, but you subtract the two, they just fall out. So we don't have to worry about the plus c when there's limits. Yep. Yep. But all the other ones we've done so far have been indefinite, so that's why there's plus c's on them. All right, last one I'm going to do today. Notice how similar this problem is to the one we just did. Pretty similar. Actually, I guess, yeah, instead of having an x squared on bottom, I got an x on top. Okay? Here's a lesson I'm going to teach you with this one, and there's a reason why it's at the bottom with not very much space. Okay? Trig substitution is a last resort, not a first resort. Okay? Is there a better option for this one before you go down the road of trig substitution? Yes. What might it be? Regular U substitution. Why is that a good choice? Well, the key is, what do you have, not what you don't have. What do you have that works nice with U substitution in this case? If you do U is x squared plus 4, you've got the piece of the du that you need. You just need the 2, and you can always put in constants, right? So you should start eyeballing things for U substitution before you ever start worrying about trig integrals or trig substitution, or as we get further, even partial fractions. Don't start with trig substitution when U substitution will do. So in this case, I would let U be x squared plus 4. du is 2x dx. So we stick in the 2 and we divide out the 1/2, or multiply out the 1/2. Multiply in the 2, divide out the 2. And so we end up with 1/2 integral 1 over the square root of u du. Here's my du, and inside here is my u. And then to do square roots, remember the easiest thing to do is turn them into exponents. So 1 over the square root of u is u to what power? Negative 1/2 du. So you got a 1/2 out front. Add 1 to negative 1/2, you get positive 1/2, so u to the 1/2 divided by 1/2. 2u to the 1/2, and the 2 will cancel with the one that's out front. forget your plus c. Which leaves me with, now plugging back in, x squared plus 4 to the 1/2 plus c, or square root of x squared plus 4 plus c. Again, don't start with trig substitution when u substitution will do. By the way, the last example, I will go ahead and work on a video for you and post it if you want to fill in the rest of your notes. But the only reason I really threw it in is because I had forgotten that I was going to do one with limits up here. I did one with limits before. I just wanted to make sure that you knew to change the limits whenever you do trig substitution. So that's this last example. It's going to be no, it's another sine one, a sine theta. I would let x be 2 sine theta in this case. Plug it all in, do all the same steps again. But again, remember to change your limits at the point you plug in to the integral. Okay? All right, with that, that's all. You have, like I said, 6 questions or so from this section due on Monday over trig substitution, and we'll start partial fractions. We'll do a smaller version of partial fractions and then dive straight into Wolfram Alpha and Maple as our real tool, our most important tool for integration going forward. All right, we'll see you guys. Have a good weekend.